All right, guys, so the topic for your notes today is molecular polarity. Today's December 11th. And guys, what I want to do is I want to set the stage for you so that you understand how this is all going to unravel. And guys, some of you, this is going to be, I don't know, like maybe a stressful experience. Because guys, what you're going to see is that your ability to connect with what we're about to do is going to hinge upon how you did on the last 2 pages of the test. So if you're good with names and angles and geometries, and you're good with Lewis dot structures, you're going to have this moment today where you go, oh, that's why we were doing these. But guys, if that's not the case, there could be this sense that you're going to be going, ooh, yeah, okay, this is not quite settling quite right with me. But guys, understand that you have time and you're okay, and remediation is going to work. And please don't get into the middle of this and go, because I can't do this completely well, I'm just going to tune out and just because I'm incapable of learning the new stuff. Because guys, you can sort of ride on our coattails right now, and we can help you through drawing the Lewis dot structures and then learn the new stuff with the understanding that you're going to remediate and get the other stuff later. You know what I'm saying? Okay, so guys, with that said, goals for today. What we're going to do is we're going to learn to connect these Lewis dot molecular structures that we drew on the last page of the test with what they look like three-dimensionally. Now guys, along the way, you don't need to know the names and the angles anymore. You don't need to know tetrahedral, trigonal pyramid, bent, straight, linear. You don't need to be able to name them. What you got to be able to do is look at them and go, oh, that's what this molecule looks like. Then guys, we're going to review really quickly polar covalent bonds. You may remember in the previous unit, we talked about covalent bonding, which is sharing, and we said it happens 2 ways, equally or unequally, and we said we'll worry about it in the next unit. That's today. And then guys, we're going to bring this all together and we're going to talk about molecular polarity, which is our goal for the day. You guys ready to go? Okay, so guys, here's how we're going to start. We are going to draw 6 Lewis dot structures. Guys, you want to make them big. Make them a couple inches across because we're going to come back to them at the end of the day. So guys, these, don't do anything yet. You don't need the examples. Guys, just draw them, but wait, we're going to do this together. So guys, these are the 6 molecules that we're going to draw, but now what we're going to do is we're going to draw them as 3-dimensionally accurately as we possibly can, and I'll go slow enough that you can catch up. So guys, the first one we're going to do is CCl4. Don't draw it yet. Let's talk. So guys, this is what CCl4 looks like. Now, let's talk about geometry. So guys, this molecule has how many domains on the central atom? 4. So what's the domain geometry? Tetrahedral. You're going, wait, I thought you said we didn't need to know that. You don't need to know the words, but we need to talk about it, which means we need words. So guys, you've got 4 domains, tetrahedral. Now they're all bonding, so what's the molecular geometry? Also tetrahedral. Guys, we don't care about the angles. What we do care about is this. This molecule is a tetrahedron, and guys, a tetrahedron looks like this, right? Or from the test, we said it looks like this. But guys, this is the closest that we can get to drawing a tetrahedron on a flat sheet of paper, and therefore that's what we're going to draw. So guys, do that in your notes. Upper left-hand corner, about 2 inches across, draw carbon tetrachloride. This is actually really interesting stuff. It's a really good solvent. It dissolves paint, it dissolves oils, it dissolves glue. We used to use this all the time to clean glassware in lab, and then we found out that it also causes cancer. So I still have bottles of it. They call it carbon tetrachloride. We don't use it as much anymore. Are you guys all caught up? You okay? Good? Not quite yet? Okay. Say again? No, you don't. But Lauren, the thing that you got to be able to connect in your brain is this actually looks like that. Okay. You guys good? Okay, so guys, carbon dioxide. I offer you this, but don't write it down. So carbon dioxide, guys, could be drawn like this. Is this a legitimate Lewis dot structure for carbon dioxide? Absolutely. Because remember, up and down and left and right don't matter, right? But now, guys, do this. How many domains on the carbon? 2. What's the domain geometry? Linear. They're both bonding, so what's the molecular geometry? Also linear. So guys, what we're going to do then is we are no longer going to allow ourselves to draw carbon dioxide like this because it doesn't look linear. So when you're drawing these Lewis dot structures, you're going to draw them just like the olden days. Last time in class. You're going to draw them like before, but then what you're going to do is you're going to ask yourself, what does this actually look like? That's domain and molecular geometry. And if your brain goes, this looks linear, then we're going to draw it linear. So guys, the trick now is we're going to draw these as three-dimensionally accurate as we can. So we're no longer going to let ourselves do this. We're going to do that. So guys, draw carbon dioxide in a linear fashion. That's the new thing that the foundational new thing that we're doing today is we're trying to make these look three-dimensional. Ford, have you been watching screencasts? So this is completely foreign to you. Okay. All right, you guys good? Can I go forward? Okay, so guys, let's now look at water. Water, we could draw the Lewis dot structure like this, and that's fine. But now let's think. This is the new part of the process. How many domains on oxygen? 4, tetrahedral. How many are bonding? 2. What's the domain what's the molecular geometry? Bent. So guys, let's draw it bent. So it looks like this, so let's draw it like that. So guys, we are going to draw these molecules as three-dimensionally accurately as we can. So we're not going to allow ourselves to do what's on top. We're going to draw it so it looks bent. Do you see how we're sort of just connecting the two? All right. So guys, you're good on water? So let's do NH3. So guys, NH3 looks like this. 4 domains is tetrahedral. 3 are bonding. So what does the molecule look like? Trigonal pyramid. So guys, we need to draw this like a trigonal pyramid. But frankly, guys, that's the best we're going to do. So we're going to call that a trigonal pyramid. And we're going to draw it as such. So NH3 then would look like this. Yeah, so technically, Caitlin, it looks like this. But to try to draw that on a flat piece of paper is tough. So we're going to let that be good enough, which is that. Got locked out, huh? Well done. Oh, so at least it was warm when you got in. Did you call the cops? No. Wow. How's your car look? So you don't really? Or you could just have a second key.
I could, but it's like brand new. So
they give you 2 when you buy them. All right. So guys, NH3. Y'all settled on that? And you're going to want to jump in, Jason, because these are foundational to what we're doing today. Okay, so then guys, HCl, like so. Let's talk. Remember, we're trying to make this three-dimensional. So 4 domains on the chlorine, tetrahedral, but only 1 bonding. So what's the molecular geometry? It's the molecular geometry. It's straight. And guys, it looks like this, and that's as good as we're going to do. So HCl straight looks like this. So then, guys, we've got one more to go. This one's interesting. This we haven't done before. So guys, CH2O, it was on the test. It looks like this. But we've got 3 domains on the central carbon, so the domain geometry is trigonal planar. They're all bonding, so the molecular geometry is also trigonal planar. Now guys, again, you don't need to know the angles, but we can still talk about them. What is the angle in a trigonal planar molecule? 120. So guys, this one we're actually going to draw with that representation. If it looks like this, let's draw it like that. So we're going to represent it with 120 degree angles. You'll see why in a minute. So guys, this is new layer to the onion. You've drawn Lewis dot structures, you've done names and angles. Now we're marrying the two together, and we're going to make our Lewis dot structures, as much as possible, represent what they look like three-dimensionally. So guys, you all good there? You're okay? Yeah? Any questions? Okay. So guys, here then is the quick transition into what we're going to do today. Please don't write any of this down. Just allow the memories to wash over you. So guys, way back when, we talked about this idea that if we have a non-metal bonding with a non-metal, and I just stole this out of the notes from a couple weeks ago, when a non-metal bonds with a non-metal, that's a covalent bond. But if the non-metals are different, they don't have the same strengths. And guys, how do we measure the strengths of atoms? Electronegativities. Take your periodic tables and flip them over. You need them. So guys, when we get two nonmetals together that have different strengths, they share, but they don't share equally. They share unequally, and this creates what we call dipoles. And again, guys, we talked about this previously. I said don't worry about it. Now it's time to worry about it. So guys, it looks like this. A dipole is the partial charge on a bond caused by unequal sharing. And this then is how we represent them. Just watch. So guys, we've got oxygen and fluorine. Oxygen and fluorine are both non-metals. By the way, guys, which is going to be stronger, just looking at the wall? Which is stronger, oxygen or fluorine? Fluorine, because as you move to the right, they get stronger, right? So guys, fluorine is going to be stronger than oxygen. So fluorine reaches out to oxygen and goes, mine. And oxygen goes, mine. And neither one wins. And so they end up doing this. And they end up sharing. But guys, notice where the electrons are. Why are they closer to the fluorine? Because fluorine's stronger. So guys, what this does, and watch, this is the big idea today. Guys, what this does is it creates what we call a polar covalent bond. Literally, these electrons are closer to the fluorine than the oxygen. And remember, guys, electrons are negative. So if the electrons are shifted to the right, that makes this end partially negative. We call it the negative dipole. The other end is the positive dipole, and we call this a polar covalent bond. Now, guys, this is how we're going to represent it. When we represent these dipoles, what we do is we draw a big old arrow. And this is what you're going to be doing in homework today. Guys, we draw a big old arrow, and then we cross this end of the arrow. So, guys, let's talk. What does the cross look like? A plus sign, because this is the positive dipole. And then, guys, what does the arrow represent? The direction that the electrons are moving. So here's what you're going to do. Along these covalent bonds, you're going to draw an arrow that represents the direction the electrons move. That is the negative end, because electrons are negative. That makes the other end the positive end, and that's the way we represent dipoles. Do you get the idea? Okay. So guys, what we're going to do then is we're going to do this with the molecules that you just drew. But guys, before we do, let's now talk about the whole picture. You want to write this down in your notes. Guys, and this is the goal for today. This is your homework today. We're just about done. What we're going to do now is we're going to talk about how these polar bonds affect the polarities of molecules. This is your goal for today. So guys, here's what you're going to do. First thing you're going to do is draw the Lewis dot structures as realistically as possible, but we already talked about how to do that, and you didn't have any questions, so I'm assuming we're good. Jason, did you get those from William? Okay. We're going to come back to them. So, then guys, step number 2 is this. You're going to draw in a polarity arrow for each bond, just like we saw on the previous slide, but we'll work on it together. Then guys, once you've accomplished that, the last thing that you've got to do is you've got to figure out if this molecule is polar. Some of you are about to have an aha moment relative to the lab. So guys, here's the interesting idea. You can have a molecule with polar bonds that isn't polar. Polar bonding does not necessarily mean symmetry. Get it? Remember in lab, huh? There's a method to our madness. So guys, when you're figuring out if a molecule is polar, what you're actually asking is it symmetrical? And the answer is obviously yes or no. So guys, it goes like this. If the molecule is balanced, symmetrical, it is not polar, and you're going to label it as not polar. Then guys, if the molecule is imbalanced or non-symmetrical, it is polar. And at that point, what you're going to do is you're going to use an overall arrow to represent the polarity of the whole molecule. For those of you that have taken physics, these are what are called vector sums. Now you're starting to get a sense of why I don't teach physics. Do you guys know that about me, that my minor is physics? Like when I student taught in college, I actually student taught more physics sections than I did chemistry sections. And I found that physics was really, really hard to teach. So when I moved to Utah, I didn't tell the state of Utah that I have a degree in physics, so they couldn't make me teach it. Now, physics is so hard to teach because everybody thinks they know what they're doing, because everybody's seen a ball fly through the air, but nobody really understands what's going on. And when you try to tell them what's really going on, they think they're smarter than you. See, the nice thing about chemistry is none of us have seen atoms, so you guys can't challenge me. We all just pretend we're ignorant and learn together. It's beautiful. Could all be lies. We don't know. You guys good? You ready to go? Here we go. So guys, what we're going to do is we're going to apply this 3-step process to the molecules we've already drawn. So we've already done number 1. We've already drawn the Lewis dot structures as realistically as possible. Then we're going to draw on the polarity arrows. Guys, what information do we need in order to draw on the polarity arrows? Electronegativities. Be ready. Then guys, once we've drawn in all the polarity arrows for the bonds, we're then going to determine if the whole molecule is polar, and that will be a function of symmetry. So guys, it goes like this. CCl4. So pen or pencil in hand, and I'm going to go with blue. And guys, we are going to draw in the arrows for the bonds. In order to do that, we need to know which direction the arrow points. In order to know that, we need to know their electronegativities. Look them up. On the back of your periodic table, guys, don't be helpless. Grab your periodic tables. On the back of your periodic table, and if you don't remember where, look at the key in the lower left-hand corner. We need the electronegativities of these atoms. What's the electronegativity of carbon? 2.55. What is the electronegativity of chlorine? 3.6? 1.6. Okay, so chlorine is bigger. So guys, don't draw yet. Watch me. Here's what that means. Carbon is bonded to chlorine, but this pair of electrons right there is not equally in the middle. Because chlorine is stronger than carbon, this bond is polar in that direction. But what about the other three bonds? Same thing. All four of these bonds are polar towards the chlorines. So guys, literally, carbon is being ripped apart by four chlorines. Carbon is being stretched in all four directions because these chlorines are stronger than the carbons, and as a result, all four of these bonds are being pulled outward. So guys, here then becomes the question. We now understand that each one of these bonds is polar, but is the molecule polar? And this is a question of symmetry. Is this molecule symmetrical? It actually is. If you hold it like this, it's symmetrical this way, and you're going, wait a minute, no it's not, because these chlorines are up and these are in and out. But guys, up and in and out don't matter. It's the same stuff on both sides. So it's symmetrical this way, it's symmetrical this way, it's symmetrical this way. This molecule is symmetrical. Now guys, if you don't like that idea, consider this. Imagine if, hey, let's try this. Grab that. Grab this. Can you grab that? Okay, now guys, imagine, this is really what's going on with symmetry if you understand vector sums. So guys, the four of us just became chlorine atoms. And remember, chlorine is pulling harder than the carbon, and don't overdo this. But what we're going to do is we are actually going to apply pull to this central carbon, and each one of us, to the best of our ability, is going to pull along the bond axis. But we're going to pull with the same strength. So guys, don't pull real hard, but each one of these is chlorines, and if we, go ahead and try, if we all pull with the same strength, is the carbon, you ionized here, yeah. But you get the idea. If we all pull with the same strengths, did the carbon move? Why not? Because all the pulls balanced out, right? Why did all the pulls balance out? Because the molecule is symmetrical. So guys, because the molecule is symmetrical, the pulls balance out. Because the pulls balance out, we would then simply come along and label this molecule nonpolar. And again, guys, the reason that it is nonpolar is because it's symmetrical. So now you're thinking to yourself, so what? Well, guys, all of the properties of carbon tetrachloride, including the fact that it's a carcinogen, link back to the polarity of the molecule. That's what we're going to talk about for the rest of the unit. We'll get there after Christmas. So guys, you good on the idea about symmetry? Yeah. Yes, but it's not, you're halfway there. You can't rely on what you said, because yes, all of them are pulling out, but the trick is they're pulling out equally. It has to come back to symmetry. That's back to Lewis dot structures, which is a step below what we're talking about. All right, guys, so let's do this. Carbon dioxide. Grabbing your periodic tables. And maybe you could do this one simply by the trend. Guys, which one is more electronegative, the oxygen or the carbon? The oxygen is more electronegative so because it's towards the right. So guys, this bond is polar in this direction. This bond is polar in that direction. But guys, what about symmetry? Just a second. Oh, wait. Go ahead.
So, since they're double bonds,
Yeah.
there be two?
No, I'm glad you said that. Guys, the multiple bonds don't influence the conversation that we're having. They change the structure, and you'll see that in the last example. Well, sort of. But they don't change the polarity of the bonds. So guys, carbon dioxide looks like so, right? Symmetrical? So if this one is pulling that way, and if this one's pulling that way, but they're pulling with equal force, what about the overall molecule? Non-polar, because it's symmetrical. So guys, this molecule is non-polar. Is that sitting okay? And guys, I wish we could sit and talk about this, because everything that you know to be true about carbon dioxide is a gas. Carbon dioxide is more dense than air. You know that because you've seen your uncle come to the family picnic and throw the dry ice in the big old vat of what's going to become root beer. And you see the carbon dioxide spill out of the top and flow across the picnic table. And you know that dry ice is made of carbon dioxide. And we call it dry ice because it doesn't melt. It goes right from the solid to the gas phase, which we call sublimation. Guys, all of that stuff that is actually true is because carbon dioxide looks like this. We're going to talk about all sorts of fascinating stuff after Christmas. I know. You guys all have that uncle, right? That brings the big 5-gallon orange thing and makes root beer. It's because you live in Utah County. That doesn't happen anywhere else. Okay, guys, so here we've got water. Hey, if you're wondering, guys, why did we talk about drawing these things three-dimensionally accurate? So, guys, the conversation goes like this. Oxygen is more electronegative than, don't write this down. Oxygen is more electronegative than hydrogen, right? Yeah, it is. And so when we draw in the polarity arrows, they would go like that. And they appear to be balanced because this molecule appears to be symmetrical, because when we draw it like this, those poles appear to offset. But then we remind ourselves that water does not look like that it is in fact bent. And then it's a completely different conversation. So guys, if you need to look up the electronegativities, you can, but oxygen is 3.44 and hydrogen is 2.2. And so this is what your drawing looks like. Draw in the arrows. Do the arrows point towards the oxygen or the hydrogen? The oxygen, because it's higher electronegativity. So guys, this arrow goes like this, and this arrow goes like this. Now, guys, water molecules, you've dealt with these many, many times. Water looks like this, right? Is this symmetrical? No. Guys, look, if you draw this dude is not symmetrical, right? So it's polar. So now, guys, this is the last step. If the molecule is not symmetrical, it's polar. Here's what you do with that. This is vector sums. You've got a vector that's going up. You've got a vector that's going left. So, guys, watch my hands. What is the sum of up and left? When up and left come together, what is the sum? The sum is up left. So the sum is, seriously, the sum is diagonal in that direction. Guys, why does water make things rust? Why is water a liquid at ridiculously high temperatures? Why does water form clouds? Why does water dissolve stuff? Why is water slippery? Everything that you know to be true about water is because of that. Because it's bent and therefore polar. Why does water expand when it freezes? Would be on the bottom. Water is the only substance on earth that it's solid, floats, and it's liquid. The only substance, actually it's one of 3 substances in the universe that's true of. But guys, water is the only substance on earth that when it freezes, it expands. And because it expands, the solid is less dense than the liquid, and as a result, it floats. Guys, every other substance on earth, like if you guys, Utah County, in addition to making root beer, y'all can food, right? And seriously, and you've had a saucepan full of wax, right? Because you can with wax. And if you've ever had a saucepan full of molten wax, and if you put in another chunk of wax, where's the wax go? To the bottom, because it sinks. Guys, every other substance on earth sinks in its liquid. Water doesn't. It's the only one that floats. Why? Because it looks like this. Yeah. Really?
What are you talking about?
I don't know what you're talking about. I mean, I guess I'm not from here, but...
Go to the canning section at the grocery store and you'll find wax. But what you do is, well, it depends on how long you're hoping to save stuff. But the problem is that many times those lids fail. And so people that are really, I'm not being offended, but people that are really serious about canning, what they'll do is they'll fill up the mason jar. And then you actually pour wax on top of that. And the wax forms a secondary seal. It hardens on top of the jelly or the applesauce or whatever you made, and it seals it. And then when you screw that lid on, you've got double protection from air getting in. You guys have never done that? Yeah, so you know the lid, it's just the metal plate that you set on top, and then the lid with the big hole in it screws on top. Many times what people do is before they screw the lid on, they pour wax on top of the surface of whatever's in the jar, and it solidifies and seals. It used to be that people didn't even have those, those gasketed lids. They would just seal their canning supplies with wax. You guys don't know this? How do you call yourselves Utah County residents?
Well, I'm not from here. I'm from Arizona.
There you go. All right, guys, NH3. So, which one's stronger, nitrogen or hydrogen? Look it up. Nitrogen is stronger? I'm not sure. I don't know. Is it 3? Oh, okay. So nitrogen is stronger than hydrogen. So guys, what direction then do these arrows point? Towards the nitrogen or the hydrogen? The nitrogen. And we have a bond like that. But there may be some examples of hydrogen bonding with some of these weaker metals down here. I'm not, but you can always look it up. So guys, now we need to talk. Is NH3 symmetrical or not? Not. Guys, it looks like this. You're thinking in your head, no, that's a trigonal pyramid. And if we draw in this plane, that is clearly not symmetrical. Therefore, the molecule is polar. And then, guys, once you've identified it as non-symmetrical and therefore polar, you then need to play the summing game. So what then is the sum of right and left and up? When these come together, what's the overall movement? Yeah, good, Kale. It's up. It's like this. And guys, for those of you, I'm sure most of you, for those of you that don't know, NH3 is actually ammonia. Ammonia is a wonderful household cleaner. The reason, guys, is because its polarity allows it to grab a hold of things like dirt and carry it away. And it stinks, and we almost died. Okay, guys, 2 more. So HCl. How do you know this thing's got to be polar? 2 atoms, and they ain't the same. So guys, 2 atoms that are not the same has got to be polar. And this is polar towards the chlorine. because chlorine is stronger than hydrogen. Guys, for reference, HCl is hydrochloric acid. Digest our food is because of that polarity. The polarity of that bond causes that bond to break very readily, which is what makes this molecule acidic. All right, guys, we got one more. Rachel, this is going to sort of get to the question that you asked a minute ago. Okay, now guys, this is tricky. Hold on, let's roll and then we'll come back and do questions. Guys, please don't get lulled into complacency. Right now, the only thing you can say for sure is that you're good at watching me do these. Guys, please don't get this false sense of confidence. These can get tricky. What makes this difficult? Well, now guys, we've got a molecule that has 3 different atoms. And so now we need to be talking about overall polarities, perhaps, for a molecule that's more complex. So guys, we need all of their electronegativities. Hydrogen, and I'm even going to write them down. Hydrogen is 2.2. Oxygen, I remember, is 3.44. What's carbon? 255. So guys, now we need to take these individually. So let's look at the bond between carbon and oxygen. Polar towards which atom? Oxygen. Draw it as such. Now, guys, we need to look at the polarity of the carbon-hydrogen bond. So carbon is stronger than hydrogen, so that would be polar towards the carbon. Carbon is stronger than hydrogen, that would be polar towards the carbon. Now guys, is this molecule symmetrical? No, it looks like this. If you just draw in this plane, you can clearly see that it's not. Oxygen and hydrogens, it's not symmetrical. So now what we need to do is we need to identify what direction all of these move. So we've got down and right, up and then, so guys, can you see that all of these are flowing in that direction? So we're going to go like this for the overall polarity. You get the idea? So, Caitlin, you had a question. The HCl, it's polar. The reason is because